Purdue University is actually is actually like focused quite a lot in developing new capabilities for robots at different scales. So we not only try to get like robots to perform the actions they are supposed to do or they conventionally do in a more efficient manner, but we kind of like try to push the design space of robotics towards new terrains, like in order to give robots the ability to make new basically to achieve new degrees of motions. And some of these degrees of motions come significantly inspired by the animal kingdom and how different animals use different like body postures and like locomotion styles that are typically ignored by the field of robotics. These fields of locomotions are particularly good in for obstacle avoidance or for moving into like over terrains that are not only complex in structure but also unexpected, meaning like the terrain that you have not seen ever before. So you want your robot to be able to adapt to these constraints from the environment, and also hopefully to be able to sense from the environment at the time that the robot is not causing any sort of major damage to whatever is nearby. So again, something quite important, this does not only happen with robots that are big, it happens at different scales. And there is a great effort from our university to get the robots to actually to get into a miniaturized size. And this has plenty of as you will see, this has like many opportunities for the biomedical fields, where you want like robots to actually serve as probes for different testings and also for repairing tissue ultimately, and also for manufacturing, especially manufacturing these kind of things that are not physically easy to handle. And I'm talking about like micro and nanostructure systems. So we hope like with this approach, robotics will be actually improving the overall capability of this country of improving in manufacturing, also improving healthcare outcomes, and to also lower the barriers of entry of robotics in general, in order to make robots more ubiquitous. Meaning like that robots that will be that you will not be scared of interacting to, and that will facilitate basically like so it's kind of like you can think of this like when cell phones were developed. At the very beginning, people thought like, okay, so this is just going to be good for communications. Whenever I want to call somebody, I will use it. And I have to say, the very last thing that I do with my cell phone now is calling somebody. So I think we're actually in the pursuit of getting robotic into that stage. Like making it so easy to access, easy to program, easy to adapt to the new situations, that it will become a stepping stone or a tool to develop like unforeseen applications. So okay, so we are going to be like providing like you with kind of like highlights of our research and kind of ideas of where we are taking or what we consider the future work, and where do we think future graduate students will become like very valuable for us to basically accomplish these challenges I mentioned. And these talks are not supposed to go into details. They are going to be brief and kind of like giving you again an overview of like what we do over here. And it is expected that most of these hours would be for you to ask about like like, do you do this particular thing? Do you think like I'm particularly interested in addressing those questions that you have at the beginning when you join Purdue, and you all have the same questions. Those are like they have the flavor of like professor, like Yeah, how much, which one is the favorite programming language that you prefer in order to do robotics? Or how much it is important for me to know simulations of things, or how much can I expect the grad courses I'm going to take will teach me this or teach me that? And again, please take this opportunity to kind of lose any fear you might have about what otherwise might be considered as a very complex field of research. And just I can tell you, everybody, all the panelists are very approachable people. You got very lucky with that, and we will be delighted to address your questions and comments. Starting from that, I think I'm thinking. Yeah, I'm thinking, Dave, because maybe we can make it scalable. So, and maybe because you start with the micro robotics, maybe in that case you will be the first one. Are you happy with that? Otherwise, I can start.
Sure, that's fine. I have a more general kind of overview of the robotics of me, which I have a couple slides on. That will work.
That's fantastic. I'll mute myself.
Okay, great.
Please go ahead.
Share my screen. Okay. Can you guys see that?
Now we can see it, yeah.
Okay. All right, so I guess I'd also like to say welcome to all you guys. Unfortunately, we can't see you in person on campus, but hopefully we will see some of you in the fall, next fall. So I'm Dave Kepler. I'm associate professor in mechanical engineering at Purdue, and I'm going to talk about the different robotics efforts here. So I'm going to start off with a highlight video, and then talk about different faculty and what their expertise is. You'll recognize some of them from the video. And then I got a list of relevant classes that we teach, and then talk about some of the research centers on campus which have a robotics theme where you might be able to get involved if you were to come here. So hope there's audio with this. So if the audio doesn't work, let me know and I'll try to fix it. So here we go.
The biggest difference between marine robotics and, let's say, ground or air is that as soon as we put the vehicle in water, we don't have information about the vehicle. We don't have the GPS. Marine robots, they perform based on a pre-planned motion. They go, they do their pattern, and then they come to surface after a certain time. They tell us, okay, I'm here. And then we get the data and we plan for the next stage. So that's the biggest challenge.
We've been working on these microscale tumbling micro robots. So these are small little magnetic bodies which we can control using electromagnetic fields. So just like you have a car tire to go over rough terrain, we can use that same kind of modality to have these robots go over different rough terrain, dry surfaces, and wet surfaces, up and down inclines.
But there's a lot of human proprioceptive controls and other things that are built into our hands and our body and our brain to talk to our hands over millions of years, literally. Right? It's sort of built into us as human beings that it's a natural way by which we have used tools, we have made things, and so on and so forth. And now using the hand to sort of be able to puppeteer these robotic constructions is pretty fun. It's very intuitive, and it's a new form of control. And the hand has a lot of degrees of freedom, so you can do a lot of things with your hand to control these toys.
We were trying to come up with a new way for robots to explore their environment, moving away from robots that walk or locomote to robots that can grow like plants or cells. It can have a power supply that doesn't need to move. It can just stay stationary, unlike a locomoting robot. That gives us a lot more flexibility in terms of weight as we move through our environment.
What you see here is one of our new designs we call the boom copter. It's called the boom copter because it has this extra propeller that rotates around the front boom.
This boom copter has been trained to identify. So we are kind of pre-programming it to do grab the door handle and open it up when it sees a door and a handle like that.
So on a bridge, if there's an earthquake, we could go there and put a sensor on the bridge, check it out, replace batteries, change lights in hard to reach locations. We could use it for inspecting and maintenance inside elevator shafts or in gas and oil pipelines for first responders to be more than an eye in the sky and actually interact with the environment, help find survivors or move things around, assemble things, or go through rubble. So basically, we want these robots to go and do tasks which are dangerous to humans. So take the human out of the loop, make it easier for them to get these tasks done where we can use the robot to do it.
The hummingbird inspired robot. These are like 12 grams. And the leaf it can generate is up to 27 grams, which is very close to the size of the hummingbird. And winning frequency is also very similar, around 40 hertz. We use all different control algorithms, reinforcement learning, AI. So we train the robot. The robot can also behave similar to the hummingbird. Control algorithm has to be robust and adaptive. Say if you have wind gusts and external disturbances, right, or bump into the wall, you can still deal with that. So the control algorithm itself should have some robustness built into that. My students are also quite passionate and interested with this research. I mean, this research itself is naturally intriguing.
Okay, so that's some little highlight videos that we have, and you can check out the ME webpage for more details. And that's also where we have a list of the faculty in robotics and ME. And so Professor Ariata, he did the adaptive structures, that earwig origami robot. Laura Blumenstein, she was with the growing robots and soft robotics person, and also wearable systems. And then myself, as Ranji's pointed out, the micro robots, small scale robots, biomedical applications, also do more some of the drones work and some agricultural robotics. Professor Sipra, he's into traditional robotic kinematics and manipulators, also some modular robotics, so reconfigurable modular robotics, so robots that can assemble themselves in different configurations for different tasks. Xinyan Deng, she was with the flapping wing robots and bio-inspired robotics. Professor Dyke, she's more into machine vision, cyber-physical systems, and the robotics aspects of that. And then Professor Mahmoodian, she'll have a chance in a couple minutes to talk about what she does, but she's in the marine robotics side. Some really cool stuff there. Professor Meckel, he is more on the mechatronics and controls, the connected vehicles. Professor Pennock is in traditional kinematics, robotic manipulator designs. Professor Ramani, he was with the glove controlled robot. He has actually a pretty neat startup company which sells those robot kits now. So more on the human robot interaction side. And Professor Yao is really a controls guy. And so lots of different control systems he does for robotic applications. So in ME, we have a list of courses we consider in the robotics area. And then also along through the College of Engineering, there's many other different courses which you can see listed here on Aero Astra or ECE or industrial robotics. And the nice thing about all these programs is if you're in the College of Engineering, you can take any of these classes and they will count towards your degree. So you don't necessarily have to take all ME classes if you're an ME. You don't have to take all industrial engineering classes if you're industrial engineering or ECE, right? You can take a mix and match. And so you can really customize your program depending on your research interests that are there. And then finally, so there's a lot of different centers that are affiliated with robotics research in the College of Engineering at Purdue. And so there's an initiative called the Autonomous and Connected Systems Initiative in the college, which is trying to kind of bring these together under one roof and really promote the activities of different faculty members and to help get industry connections for these. So on the top left, there's this is the IoT for Ag, is a new engineering research center funded by National Science Foundation. So Purdue is a partner with 3 other universities, and this is for agricultural robotics. So can we come up with ground robots and other robots to really help improve the productivity and yield in different kind of farms. The REF Institute, this is Resilient Extraterrestrial Habitats. This is NASA-funded institute where we're trying to design resilient structures which can be in space or on Mars And then if something goes wrong, we want these robots to go out and do the repair and maintenance of these structures so it's safe for when the astronauts get there. Aspire, this is a new engineering research center as well, funded by NASA Science Foundation. This is on connected vehicle technology, connected roadways. We have the Center for High Performance Buildings. This is on smart buildings and how can we use automation and robotics for smart construction and for data analysis and to really value the state of these buildings and how they maintain them. ICON is a new center, internal center, which is just launched on the Center of Innovation in Control, Optimization, and Networks. So a lot of network sciences with approaches to robotics, sensor networks, networks of robots and how they interact. Then we have the JTRP, which is a Joint Transportation and Research Program, which has a lot of work with connected vehicles and connected roadways. And so there's a new project with the Federal Highway Administration on a connected corridor on I-70 between Ohio and Indiana. We're going to use that to connect the roadway to vehicles and what can you learn about the roadway and the vehicles from all the exchange of data. And it aligns also with the NextCar initiative, which is a consortium of the other companies along with ARPA-E funding to do platooning of Class 8 trucks. So you have one driver and a leader follower, and the leader driving the truck, and the second truck is platooning following it with autonomously. And so they're trying to work on that. So these are kind of initiatives where you could kind of see yourself hopefully joining one of these groups if you're here. Okay, so I'm gonna pause there and turn that over to Nina.
Yeah, so this has been very complete. And Nina, do you want to be next? I think your work has been already like introduced a little bit, and it will be the right time now. Nina, can you hear us?
Sure.
Oh, perfect.
Yes, I can, and thank you very much. Dave, you did a great introduction to what we do at ME. So it was very comprehensive. But to add that, I mainly focus on persistent autonomy in challenging environment. And the environment can be on ground, air, between air and ground, or mainly I focus on water because it is the most challenging environment to deal with, and it is the least explored domain out of, 70% of Earth is covered with water, and we don't know much about it as much as we know about other domains. So that's why that I focus on marine robotics application and maritime sensing. We develop really tools to lower the cost of operation from different aspects. We want to bring down the cost of robots, as Professor Martinez mentioned, to bring down the barrier of entry and use of the robots. We also want to make them efficient from the perspective of energy autonomy, so that we don't need to have human in the loop to deploy the robots and then recharge them and get data out of them. And we also want them to be able to cooperate and coordinate among each other so that we can deploy multiple robots. And we also are interested that different robots, let's say from water to air to ground, be able to coordinate to each other. So that's what I contribute, what my group focus on, to really create a persistent network of robots that they can work together in different domains.
Nice. All right. So so kind of like to recapitulate, like, so we have like basically robots. Just for you, so you get for all the students to get a taste. So we have robots that actually like move in like on Earth. Definitely we do a lot of like robots that fly, all sort of like drones, collaborations between like robots that fly and those that are going like on Earth. And now like this capability of have robots capable of swimming and coordinating swimming motions, and then like also get to establish collaboration with other robots that have other sort of locomotion plans are very important. So so it's kind of like just don't think like this, especially for the students, don't think that there is a particular thing that we don't do for a reason. So we do kind of like everything, like moving any robot, moving on any sort of surface, and in my opinion, at any scale. So like from the micro scale to the like you know, to robots that are like definitely quite big, to robots that you could ride potentially. So I'm just gonna show you a little bit, like this is going a little on the, let me first try to figure out how to properly share my screen. Screen sharing, okay, we should be all right. Okay, and this is kind of like, so I want you to know that like we are not only exploring how to make robots that are actually better than the ones that we currently have available, or the ones that we are kind of like used to deal with, but we do a lot of research in terms of how we can use the new advances in materials to enhance the functionality of current robots, or to basically come up with robots that exhibit certain functionalities that are quite atypical, let's say, when compared with conventional systems. So I'm just gonna go very quickly. So my line of research is mostly focused on soft robotics. And soft robotics is kind of like moving away from the conventional robots that are made of like completely rigid links and having like a well-limited, a well-defined number of connections, and going into a body plan that looks more like an octopus, meaning like continuous deformation and basically like deformation all over the body. So these robots are made of elastomer, and they are kind of like, this is the elastomer. We make molds with the 3D printer, we cast the elastomer, and basically we make pneumatic channels inside, so they inflate kind of like party balloons. So, but rather than just inflating like a party balloon, we just put like different, we call them strain limiting layers. And these guys are gonna be avoiding like this situation where you are expanding in all directions and making your actuator bend in a particular direction. Why is that useful? Well, that is useful because if you work on your design a little bit more, you get to make very inexpensive grippers, which are very useful robotic actuators that can be operated just by using pressurized air, which is something that you can get from the environment and is also environmentally clean. And you can operate the different fingers just by inflating each of the channels that you have inside the soft robotic actuator. We are using polymers that are biodegradable, and this is actually bringing a new dimensions. Before, whenever your robot was broken or one of the fingers was not working as necessary or as expected, you had to fix it. And actually fixing robots like it requires time and it is expensive typically. Over here, you can just like discard these guys, you can burn them, and then they will basically generate no byproduct after being burned. And you can just like plug one in because the components are so inexpensive that it is actually quite nice to just like deal with these technologies, like kind of like single use, if you want to think about it like that. Then by just like playing some tricks, I will not go into the details, but we made these robots to behave as or to replicate certain high speed motions that are available in nature. I'm gonna show you this if I get to change the, no, I think, nah, my graphic card gave up on me. I'm afraid I will not be able to share with you. So all these videos are in my YouTube channel. I'm very sorry for that. Yeah, right now I cannot see you. I know that you can hear me and see me, but it's just like my camera is misbehaving. YouTube channel, and you will see how we make these robots out of rubbers that behave like, can I? No. that can mimic snake-like locomotions or striking, capturing events. Like, for example, we were able to capture alive beetles just using an actuator that can unroll in the blink of an eye and then capture the beetle alive. And we have, let me see if I get to play this before I'm done. Yeah, and we even play with the structure of different actuators in order to create or to bring new degrees of motions that are typically forbidden in kind of like in soft actuators, meaning like doing linear motion is fine, but doing rotational motion, it is actually much more complex. So we achieve that by playing with the actuators. That being said, again, there is a lot of effort that will not be only, so don't think that coming to Purdue to do robotics will keep you programming all the time. Sometimes that will be the case. I mean, like your robot will require some programming, but it will not be the only thing that you will have to learn. There are gonna be all sorts of like computer vision algorithms that you will learn too. You will learn about materials, how to use them properly, how to manufacture things, how to do micro manufacturing. And you will also get the idea of how the design of your robot is ultimately the one responsible for the final characteristics and functionality of your robot. And you will learn different computational tools that will allow you to optimize your robot even before you get to fabricate it. So because my connection has been a bit unreliable, I'm trying to cut my setting the screen. Yeah, I actually don't. Okay, stop setting. If I could have another click, and basically what I want you all to know is that this is the end of our talks, and we are expecting you to ask questions. Okay, so again, there is no any silly question you can ask, because we do love to have the opportunity to nurture the students and to kind of like address those particular questions that are that you will not find on the website. Okay, so those particular questions about like, is it really necessary this or this other thing? Yeah. So, okay, so that being said, can you please, let's get started with the questions, and please, any question will do. And Dave, I cannot read now the chat, so if somebody doesn't want to get in line and just want to ask the question on the chat, like if you can read it, it will be great. As soon as I get to recover, I'll be back with you.
Okay, so I see one question in the chat. It is, what is the main issue for current soft robotics? So Ramsey,
Okay.
maybe that.
Can you hear me?
Yes.
Oh, okay. Yeah, so soft robots, because of the intrinsic limitations of their constituent material. So basically the problem is that if you want to make soft robots, you need to use either very soft or very flexible materials. And these soft robots are actually very convenient to ensure that there is safety between humans and robots, okay, which is more difficult to guarantee with other sort of robotic plans. However, these materials bring some limitations. For example, the most important parts are the fact that soft robots do not get to move fast, and also they cannot apply large forces. So there are many approaches in which we are focusing now on the development of new mechanisms that will allow us to change the stiffness of a robot. So meaning like a robot that will be very stiff in one situation, but then it can smoothen its structure out and then get to basically get as soft as necessary. Kind of like think of kind of like turtles, like or like you know, these different animals that can actually turn from something quite solid and impact resistant into something more soft and maneuverable. So I would say that those are the main, those are the main issues. I would say together with the capability of getting robots to morph. So so if you want to picture one of the milestones that is currently not quite there or not quite achievable for soft robots is to have a robot enclosed in a box, have this box with a small pinhole, and get your robot to travel through that hole. So being able to have a robot that is capable of identifying an obstacle or a very small hole and to morph its shape so that it can navigate through that is another milestone we are currently working on achieving. Okay, what other questions do we have?
Excuse me, can I ask you something?
Please.
Okay, hi, Professor Martinez. Hi, everyone. It's glad to see you again. So my question basically is, as you know, I was lucky because you were my mentor. So because as you know, we work on bioelectronics, but I would like to know, is that possible to mix bioelectronics with bioinstrumentation area, you know, such as IoT application or sub-robotics, something like that?
Yeah, so like a comment over here. Sometimes you want to, like, I can tell you the fact that there are so many faculty members working on robotics at Purdue is actually telling you that that whenever you take your courses, and this was like nicely pointed out by Professor Capillere, it's you don't need to be taking all the courses from one department. There are many departments that will be offering you possibilities to get your curriculum better tailored to whatever application you have in mind. So, for example, we have collaborations with the BME department, with Biomedical Engineering, and there are basically collaborations with everything, like agriculture, mechanical, electrical engineering. There is like many people developing different types of technologies related to robotics and applying robotics to different problems. So that being said, if you have a particular thing that you would like to learn, and I'm talking, for example, like if you want to develop like some flexible electronics, flexible electronics are now very useful for many different applications. Soft robots require to have embedded flexible components in order not to compromise the flexibility of the body of the robot and therefore their movements. But there are also many other rigid robots or even drones that could benefit from conformal sensitive skins that will provide them the capability to distributively feel or have a exteroceptive sensation of like which ones are the object that they are in contact with. So all these themes, again, are gonna drive you to a field that is not just robotics. It's gonna be, is definitely much more multidisciplinary than that. And I think, again, the presentation you saw at the beginning is definitely bringing this, remarking this point. So with your advisors, always try to address, it's something that is very valuable for all of us. It's like whenever you join Purdue, we do want to give you the opportunity to do what you want. Okay, of course, we are gonna be supervising your trajectory and ensuring that you accomplish the milestones that we have designed for you. But the best way for us to keep you motivated is that you tell us which ones are your expectations, and basically so we can kind of like draw a line in which like both of the parts are happy. So so if there is a particular application that you would like to get experience in for your future jobs, just communicate that to your advisor, and there will be plenty of opportunities to get your robotic experience tailored in that regard.
Thank you, Professor Martinez.
We got a couple more general questions, so I just want to try to get to those. So one question is, I'm going for a BS and ME in computer engineering. Which masters would you recommend to be better prepared for the robotics industry, ME or computer engineering? I'm planning for the 5-year master's. Okay, so I'm assuming that means +1, because a master's degree is typically 1 or 2 years. So I guess I would say either would be a great preparation. It depends on what area of robotics you want to focus in. So robotics is very interdisciplinary. If you like more of the programming side, I would say computer engineering and algorithm development will be computer engineering. If you're looking more electromechanical systems, mechatronics, on the control side of things, I would say mechanical engineering. What would also iterate is that in either one, if you were at Purdue, you can take classes in the other school, right? So you can take computer engineering classes if you're an ME, and if you're a computer engineer, you can take ME classes. So you can really kind of mix and match to your best interests. So, and when you're looking for jobs, typically in robotics field, it'll say bachelor's, master's in mechanical engineering, electrical engineering, computer engineering, or related field, right? So as long as you have that experience and background, you should be fine. And I guess the next question was, the courses need to be aligned with your research, or can you branch out? Kind of related to that. Yes, and you can take courses that interest you, and that's fine. It should, we don't want you to be taking basket weaving, but you should be taking something that is, in the technical area. You have certain, I guess there's not too many required classes you have to take. Typically, you will structure them for your research to help you with research, but you can branch out and take other classes that you find interesting, as long as your advisor is fine with it. Let's see. Nina or Ramses, please jump in if you have any other inputs on these questions.
Yeah, so yeah, it is. So yeah, I think it's good to. So the other thing that you can do even before joining Purdue is to contact people. So we dedicate a lot of time to address questions from our students. So just please don't feel bad to say like you can email anybody, any faculty member, and say like, Professor, I'm really interested in this particular thing you're doing. Like I would like to just like talk to you for 30 minutes. So I can ask a couple of questions I have, and then like people will be able to drive you better, and you get like more insight than what you will get probably only from the website. Even though our websites are very like to provide you with the information you need, but don't hesitate to ask. Like that is something that. It's a tradition that is getting lost a little bit. So, but I do recommend you to be proactive, and yes, yeah, why not? I mean, again, we are all nice people, so.
I would also iterate, a lot of people's websites, mod included, is not as up to date as we'd like it to be. So reach out. There's probably projects which people are working on which are not on there. Probably the easiest way to figure out what people are working on most recently is look at their recent publications, because those are updated more frequently than web pages.
Mm-hmm.
Yeah, Google Scholar might be a good indicator of recent publication, not the faculty web page, but the Google Scholar, because that's usually synced with other resources that the papers are published.
Yeah. Okay, there's a couple questions on what are you looking for in master's students, or what are you looking for in PhD students, what qualities or experiences? So obviously, I mean, having experience is great if you have some experience in robotics areas. So if you have any experience, it could be a class project, it could be a senior design project, it could be an extracurricular team, club team, or undergraduate research. Those are typically nice traits to have. Also, just the dedication to working hard and learning new things is important. Now, different labs will have different skills that value more or less. It kind of depends on the professor. So again, I would encourage you to reach out to those faculty members you're interested in looking and working with, and find out what's important for their lab.
So yeah, if I can take on this one, so I would suggest that. So there are a couple of things you need to keep in mind. One, master programs are actually okay. So some people, some grad students or like some new students coming to Purdue think that a master program is going to be easier, and just because it's shorter. And there is something important over there. They are typically not, because it's not that they are more complex or anything like that. The problem is that you have less time. So, and less time with the very similar expectations. They are expecting you to do research and to do it well, and you will have a lot of courses to complete. So one of the abilities that I actually search a lot when I'm trying to hire a master students is actually to have people that can organize themselves very well and that have like a very high self-discipline. Okay, that is something that you definitely need to get in order to be able to learn all the things you need to learn and still be productive at the lab. So in the other thing is, as you have seen, the robotics that we do over here is kind of like is very new. So definitely, if you have any sort of experience programming, or if you know how to simulate materials, or if you know how a little bit, if you know even a bit of robotics, it does help a lot and is considered like positively. But I think what we consider very highly is the capability to adapt. Okay, so because you're going to be coming to a new environment and like, which Purdue, you need to be able to cope with many different projects, because you will not be only working on one thing, you will be also collaborating with other people and getting involved into other projects that will be giving you a much broader view of what the field is in terms of robotics and will ultimately make you learn more things. So being adaptable, being proactive, and being able to just say like, okay, I'm gonna be like doing this research on my own, so I get to see if I can address this problem before I have the next meeting with my advisor, which might be in a week or so, because your advisor happens to be very busy. So those traits are the ones that will bring you success in general in the future. But again, those are the ones that we kind of like search here at Purdue too. Nina, I don't know if there is any particular skill that you are searching in your students. Can you please comment?
So yeah, I agree that I like motivation and self-discipline. That's the most important thing, traits in the grad students. And then after that, but if you bring more skills, the more you bring the skills, the better. And also self-learning. You know, some students don't come with the background, but they are very quick learners. They are very motivated to and open to learn new skills. And that's I think very, very important, because even if you come with background, you're going to see that every day there is something new that we need to learn and adapt, and that's part of the job, not only for you as students, it is for us as faculty, and that's what we want. We want people that they can adapt with new situation, and then people that we can trust and in long term become collaborators.
All right.
I totally agree.
Yeah, thanks. So I think from our organizers here, I think we have to, in the interest of time, we have to move on. I think everyone has other appointments to get to for the schedule. So I guess I would echo, what Nina and Ramses have been saying. Please reach out to us. We're not going to bite. If you have questions, email us or any of the faculty. We'd be happy to talk to you and hopefully see you guys on campus.
I hope so. Yeah, and I hope like the situation gets normal soon, and then you will be able to just like do your research and get the full experience that you can get from Purdue, which is like what we are we can really not wait to get back to normal and to get close to our students again at the lab, especially at the lab, I would say. Okay, so thank you very much, everybody, for attending this meeting. Thank you very much for the speakers for their time, and it has been a pleasure. Again, as Professor Capilleri said, like I really hope to see you soon in campus. All right, thank you all.